move for the second speaker, we're very happy to have Niccolo Cribiori from Munich, and he will tell us about Swampland constraints on scale separation and distance in 4 and 5 dimensions.
Okay, so thank you to the organizers. It's my pleasure to present this work, which actually I'm going to present some results which I worked on in collaboration with different people, with Gianguido Dall'Agata and Fotis Farakos in Padova, with Carmine Montella, who was a master student in Bologna, and with George Trikas, which is a postdoc now in NC. So, as a starting point, we all know that Swampland conjectures are indeed a window into quantum gravity. And in fact, the very existence of the conjecture is telling us that there is a non-trivial ultraviolet and infrared mixing. In particular, this is true because Swampland conjecture are, by definition, supposed to encode consistency conditions on low energy effective field theory, which are not obvious from an IR perspective. And typically, the one way, at least, to make progress into the Swampland program is to first propose some conjecture and then to really test this conjecture in top-down constructions in string theory. And this is an extremely important job because it's perhaps the only way we have at present to really gain confidence into this conjecture. So this is a really a high priority job. However, this is not what I'm going to present. I would rather try to present an alternative, a complementary approach. And in particular, the logic I will follow for this talk is the following. I will not question the validity of conjectures. Actually, I will assume conjectures to be valid, so to be principles of quantum gravity, whatever quantum gravity is. And then I will apply them directly to effective field theories. In particular, I will apply them to supergravity theory, so it's not any possible effective field theory, in 4 and 5 dimensions. So this is an approach which is purely bottom-up in this sense. And of course, you can complain always that this strategy is brutal, is coarse. But the reason why I'm presenting this work is because this strategy eventually leads to results which are not completely unrelated to the Swampland program itself. So this strategy seems to be to be pointing towards the same directions as the complementary strategy, so the top-down strategy. In particular, I will focus on 2 aspects which are phenomenologically motivated. I will motivate them later on. One is the existence of vacua, which are with a property which is called scale separation, and the other is the existence of de Sitter vacua, which was the main topic of the previous talk. And since I'm not testing conjectures, I'm using directly conjectures. Of course, it's preferable if I start with a conjecture with more conjectures which are already robust by themselves. For this reason, I will mainly concentrate on one Swampland conjecture, which is one of the most tested conjecture, which is the weak gravity conjecture. Actually, I will use the so-called magnetic statement, which is the formula here, which is the statement that the naive ultraviolet cutoff of the effective field theory is not really what you might think, but is actually lowered or is bounded by the gauge coupling. So here I'm assuming to have an effective field theory with possibly a abelian symmetry. And then what the conjecture is saying is that the cutoff has to be bounded by the gauge coupling in Planck units. So essentially, the basic idea is to take effective field theories, so supergravity theories in 4 dimension and 5 dimension, and apply this formula and see what are the consequences. Actually, this idea can be understood really from a very basic example, which is the one in this slide. So all the rest of the talk will be essentially a more elaborated version of this example. Probably the simplest example I can use for this strategy is to consider 4-dimensional supergravity, n=1 supergravity, which is the simplest theory in 4 dimensions. And I will consider only one vector multiplet, so no chiral multiplets and no scalar fields. Even though there are no scalar fields, I can generate a scalar potential which is everywhere constant by doing a deformation of the theory, which is called a Fayet-Iliopoulos term. So Fi is for a Fayet-Iliopoulos. So this is a well-known deformation. It's a very simple construction you can implement, and the result is that you have a positive, everywhere non-vanishing scalar potential. Here, psi is the deformation parameter and G is the gauge coupling. The reason why it appears a gauge coupling here is because in supergravity, you can understand a pure phi helio plus term as the gauging of the abelian symmetry in this case. Now, from this very simple formula, so I'm just looking at which are in fact related. First of all, the limit of a very small but positive cosmological constant leads towards the restoration of this symmetry parameterized by this gauge coupling. So in this particular case, is a U1R symmetry. So we are going towards the restoration of a global symmetry, and this is something which is believed not to be possible in quantum gravity. So there seems to be some problem when I'm taking this limit. But even if I'm not taking any limit whatsoever, if I assume psi, which is the charge, to be quantized, which is some natural assumption in quantum gravity, and it's also motivated by this paper here, well, then what this formula is telling me is that the cosmological constant is really of the same order of the gauge coupling. There is no other parameter I can use to decouple these two quantities. And then if I enforce the weak gravity conjecture, I see that the cosmological constant is in fact of the same order, or even slightly bigger if I really enforce that very formula in the previous slide. So slightly bigger than the ultraviolet cutoff of the theory. Now, as I will motivate further later on when I'm considering the sitter vacua, once you are in a situation of this kind, in which your cosmological constant in the sitter is of the same order as the UV cutoff, this is typically problematic because the cosmological constant will be somehow a proxy for the IR cutoff. So here I'm saying that the UV cutoff and the IR cutoff are of the same order and cannot be decoupled. There is no parametric separation between these two scales. So typically, corrections which enters at this scale will be seen by the full effective field theory. So the message from this slide is that there are these two ways which are very much related to argue for this sentence. So for the fact that pure phi heliopolar terms are in the Swampland. And this is a conclusion which was already reached by Komogorski and Seiber by essentially exploiting somehow a different version of the absence of global symmetry. So this is essentially the basic mechanism I'm going to apply for scale separation and then for the sitter vacuum. In particular, I will concentrate on models with more than 8 preserved supercharges, 8 or more actually preserved supercharges. I will give you the discussion for 8 supercharges basically, but in the works we have done during this year and the past year, we also consider higher supercharges. In particular, we'll focus on all possible gauge supergravity with supersymmetric anti-de sitter vacua. By all, I mean I will not put any restriction on the gauge group, so the gauge group will be generic. And in this setup, I will put constraints on scale separation, on the existence of scale separation, this kind of vacua. And then to address the sitter vacua, I will need to introduce some more assumptions. So here, in the case of the sitter, because I lack supersymmetry, I lack the tools that I have for anti-de sitter, I will need extra assumption, which I will introduce in due time. And of course, for this talk, there will be always a caveat, which will always be present, which is the fact that the weak gravity conjecture, as it is, it has been formulated in flat space. And I think it's fair to say that at present, the extension to a space which is not flat, like an anti-de sitter or de sitter, is not clear. There are some, for example, some recent proposals for anti-de sitter by these people. However, for this talk, I will use a working assumption. So the fact that a relation of this kind more or less holds also in a space which is not flat in the sense that I will expect, of course, correction to this formula, but I will expect this correction, or I will assume these corrections to be small when I'm in the supergravity regime. So when the radius of the de sitter space or the anti-de sitter space is big. Okay, so I will start from scale separation then. So what is scale separation and why this problem is of interest? On the one hand, we know that there is no experimental evidence for extra dimensions. On the other hand, we know that critical string theory requires extra dimensions. Actually, we can try to put numbers. So for the typical length scale of the observed dimension, we can take the Hubble scale of our universe, which is roughly some 10 to the 27 meters. And the length scales of the non-observed dimensions, of course, we don't know it. We can try to put estimates by several arguments. For example, if you say that if you observe that we don't see extra dimension in colliders, then you may want to say that there is an upper bound given by the energy of the colliders. So it's some 10 to the minus 18, but this can be changed if you use other kind of experiments. It can go up, I think, up to 10 to the minus 6 or so. Anyway, there is a huge difference between these two fundamental scales of natures. And this huge difference is called separation of scale. So there is an hierarchy in nature, which we would like to explain from first principles. And this explanation is needed whenever we would like to use effective field theories, which are not 10 or 11 dimensional, to describe our universe. So whenever we would like to use 4-dimensional effective field theories to describe our universe, then we have to be sure that the theory is really 4-dimensional and not secretly higher dimensional. What I will have in mind for this talk is the standard paradigm of string compactifications, in which I start from critical string theory and then I compactify on a space which is compact and small. However, there are alternative scenarios, like for example, brane worlds, or in general scenarios with large dimensions, which can be dark. I will not really address them. I will strictly concentrate on compactification of string theory on a compact and small manifold. So a more precise definition of scale separation for this talk is the statement that on the one hand, we have a natural scale given by the vacuum energy, so what I will call the Hubble scale. On the other hand, we have the Kaluza-Klein scale, which is the scale at which I start seeing the extra dimensions. And then scale separation in this context will be the requirement for this talk that the ratio between the Kaluza-Klein scale and the Hubble scale is parametrically small. So I will really ask for parametric scale separation. Of course, this is a first level of investigation. Then you can try to refine this by refining this ratio and really putting numbers. But for this talk, I will concentrate on the case in which I have a parametric statement. And there is, of course, a complication related to the Kaluza-Klein scale. So on the one hand, to calculate the Hubble radius, I can just calculate the vacuum energy of my theory. To calculate the Kaluza-Klein scale is a much more non-trivial problem. What typically is done in the context is to take more or less the volume of the compact manifold as a proxy for the Kaluza-Klein scale. This can be true in several cases, but there are also instances in which we know there are other effects contributing to the Kaluza-Klein scale, which are changing this estimation. And moreover, we also know that there are really Swampland conjectures directly against, or that are directly relevant for scale separation. There have been various works in the past. If you try to summarize them, probably you will end up with a statement of this kind, saying that the Hubble scale cannot really be decoupled from the Kaluza-Klein scale. So there is an order 1 parameter entering the relation and coupling them. And actually, the strongest statement is that this parameter is order 1, is 1 in fact, so that these two scales are one and the same. And this is true in certain known string theory diagrams. On the other hand, it's true that there are proposals for counterexamples to such a statement with alpha equal 1. Probably one of the most well-known class of counterexamples is the so-called DGKT class of vacua, after the authors of this paper. This is a class of compactification in massless type 2A supergravity on Calabi-House. More recently, other constructions related to this have been investigated and proposed. For example, we investigated and proposed a double T-dual version of DGKT in massless type 2A, and also with solutions allowing for an uplift to M theory. And other classes, similar classes in the spirit to DGKT have been constructed in 3 dimensions, but I will not really enter this discussion, just to give you an overview of the models which are there present. So given that on the one hand, we have Swampland conjecture saying that there should be a constraint on scale separation. On the other hand, there are possible counterexamples to these conjectures. I will not really assume any relation of this kind, but what I'm going to do next is to derive, or to show you, to give a recipe on how to derive a relation of this kind with alpha equal 1 in engaged supergravity and using the weak gravity conjecture. So the idea is roughly the following. It will be schematic. I will not give you really a precise formula for what concerns supergravity. So the real supergravity formula are much more complicated. They have indices and various quantities which have a precise role in the context. I will not show you this. If you are interested, I can give you more details, but I think it's better to explain more or less the logical steps. So I will consider, as I was saying, gauge supergravity with supersymmetric anti-de Sitter vacua in 4 and 5 dimensions and with at least 8 supercharges. So in particular, n equal to in 4 dimensions. Now, it's a general fact that the Sitter vacua that the vacuum energy is given by the gravitino mass. So this is always a starting point. And then this is the point where I need at least 8 supercharges, because with at least 8 supercharges, I have various algebraic identities which allow me to exchange the gravitino mass for some gauge coupling. For example, if you do 4D n equal to 2 supergravity, this is to special geometry. If you do 5-dimensional supergravity, minimal supergravity, you have very special geometry, but more or less the logic is the same. So you can trade a mass for a gauge coupling. So you can rewrite the vacuum energy now in terms of a gauge coupling, which is towards the desired direction to apply the weak gravity conjecture. And there will be always a charge also. So when I'm writing G, this is really the product of the gauge coupling and the charge, but I'm putting the charge to 1 just for simplicity, or you can think that the charge is quantized, so I cannot really count the charge. Now, once I'm doing this step, to really make progress, I have to understand what is the gauge group. Now, this question is in principle model dependent, because it depends on the particular matter content I have in the field. The matter content is giving me the isometry of the scalar manifold, which I can gauge, and then in turn the gauge group. So in principle, this question is not an easy one. However, there is a way out for our purposes of scale separation, thanks to this nice work by Louis Lucenruter, which showed on a fairly model-independent way that on supersymmetric anti-de Sitter vacua, the original gauge group, whatever this is, on this kind of vacua, it splits into 2 factors. And this is model independent. This mechanism always happens. The first factor, which I'm calling HR here, is the group which is really gauged by the graviphoton. And by graviphoton, I really mean a combination of vector fields and a scalar field X, which are entering the supersymmetric transformation of the gravitino. So the gravity multiple, essentially. And then there is another factor, H mat for matter, which is gauged by the other vectors, the vectors which are entering the supersymmetric transformations of the matter multiple. Now, the form of this group is actually model dependent, so I cannot say anything about this unless I studying a specific model, but the form of this other group is model independent. And in 4D and 5D is calculated by these authors to be this group, essentially. Here, n is the number of supersymmetries. So if I'm doing n equal to 2, you have to put n equal to 2 here and here. So it means that we know part of the gauge group, but this is enough information for our purposes, because then what happens is that there will be always a splitting to the contribution to the vacuum energy of this kind. So the contribution will always split in this way. I will always have a contribution from the group gauged by the graviphoton and the other group. And then I can always write an inequality of this kind by neglecting this contribution. Once I'm here, I can take just the absolute value. So what I show is that the vacuum energy is actually bounded from below by the gauge group, by the gauge coupling given by the graviphoton. And then I will apply the weak gravity conjecture with respect to really to this gauge group only. So I don't really need to know what is this gauge group. I only need to know that what is this, and this I do know thanks to this analysis, and then I can apply the weak gravity conjecture with respect to this. And actually for the minimal theory, so for n equal to 2, sorry, for the minimal theory in 5 dimensions, which is n equal to 2, this group is really abelian, and also for the n equal to 2 supergravity in 4 dimensions. So when I really have 8 supercharges, this is really an abelian gauge coupling, and so I can really apply the original formulation of the weak gravity conjecture with an abelian gauge coupling. When I have more supercharges, I can still try to work out this kind of argument by applying the weak gravity conjecture with respect to a Cartan subalgebra of the full gauge group, which is preserved in the vacuum. However, we end up with this relation saying that the cosmological constant is bounded by the ultraviolet cutoff. Then, since I'm doing supergravity, a natural estimation for the ultraviolet cutoff is the Kaluza-Klein scale. So this relation means essentially that there is no scale separation in this kind of vacua. So we proved this in 4D and 5D for the theory with 8 supercharges and for the theory with 32 supercharges, which is the maximal theory. Proving this, we believe that there is no really any obstruction in improving the same argument for all the amount of preserved supersymmetry in the between, so from 8 to 32. And also we don't see any obstructions in going beyond 5 dimensions. And if you want to be a bit more brave, let's say, you can try to combine these results with other works, again, based on the weak gravity conjecture, saying that there should be no, that any non-supersymmetric anti-de Sitter vacuum is unstable. So here, this work will cover the non-supersymmetric part, and then combined, this probably points towards the fact that there should be really no effective field theory in anti-de Sitter strictly lower dimensional. However, there is a big caveat here, a big corner which I'm not covering, an important corner which I'm not covering, which is the case with 4 supercharges. This means, for example, n equal to 2 in 3 dimensions and n equal to 1 in 4 dimensions. And this is really the corner in which the counterexamples in string theory was mentioned before are present. So this will be really one of the most interesting future directions of research. Okay. Now, before going to the sitter, I have just one slide to present a another argument related to scale separation, but which doesn't use the gravity conjecture. Nevertheless, I think it fits nicely this discussion. So this is an argument a bit more speculative than the previous one, which uses the species scale instead of the weak gravity conjecture to provide an ultraviolet cutoff. So the species scale is a notion of ultraviolet cutoff, which is defined if you want as somehow a renormalization of the Planck mass. So what the species scale is telling me is that the ultraviolet cutoff is not really the Planck mass whenever I have gravity, but it's the Planck mass divided by some power of the number of light species I have in the theory. Now, the way I'm going to use this is the following. I will be in anti-de Sitter, in supersymmetric anti-de Sitter, and in particular, supersymmetric anti-de Sitter with a known CFT dual. In these cases, I know that I have a central charge in the dual theory. For example, here, this slide is in 5 dimensions, so the CFT will be in 4 dimensions. And then I will assume that the central charge is somehow giving me a proxy for this number of species in the dual theory and also in the gravity side. Then I know from ADS CFT that the vacuum energy is given by a certain power of the central charge. So what I can do is I can combine these 1 and 2 relations and put then the expression for n does obtain into the species scale. So what I find if I do this simple algebra is that the species scale is really given by the Hubble scale, again, with no other parameter entering the relation. So if you really want to use the species scale as a ultraviolet cutoff for this kind of model, then again, you are ending up with a relation saying that the ultraviolet cutoff and the Hubble scale are of the same order and cannot be decoupled. So the same conclusion as before with another kind of reason. Now, in the remaining minutes, I will concentrate on the Sitter vacua. So the discussion will be similar as the previous one, but a bit less general, because essentially without supersymmetry, I will need more working assumptions. So let me start by giving you an overview and a motivation for this investigation. On the one hand, as for scale separation, there are experiments which are telling us that there is some dark energy which seems to be compatible with a cosmological constant, with a positive cosmological constant. On the other hand, there is no universally acknowledged construction of the Sitter vacua from string theory at present. And there is not even consensus among the most studied scenarios, for example, KKLT or LDS. And more in general, if you try to study the Sitter vacua in supergravity in any kind of dimension with any kind of matter content or caging, this is a really hard problem. There are very few examples which are available in the literature. So given this situation, I will try to remain agnostic again about the precise microscopic model. I will again apply a purely bottom-up approach. I will start from supergravity and I will apply to supergravity the weak gravity conjecture. In particular, of course, we will not assume any Swampland conjecture against the Sitter vacua, for example, the so-called de Sitter conjectures. Rather, I will put constraints on the Sitter vacua by means of the weak gravity conjecture. So, The starting point is again the scalar potential of the theory, which is schematically of this form. So if you do gauge supergravity, there will be always two contributions to the scalar potential. One is positive, which is given by the gauging. This contribution is breaking supersymmetry. The other is negative, which can be supersymmetry percent mass. Now, I would need to assume that the gravitino mass is vanishing on the vacua I will be, on the critical points I will be considering. So we'll assume from now on that this term is absent for some reasons I am not interested in. Then, if this term is absent, I can really play the same game as before, because then my vacuum energy will be really given by truly a gauge coupling. Then I can split the gauge coupling into two contributions, one coming from a group which I will be then identified with the group of the weak gravity conjecture, and the other with the rest. Then I can always neglect the rest part and apply the weak gravity conjecture to reach a statement of the type that the cosmological constant is bounded by the UV cutoff given by the weak gravity conjecture. Now, once you are here, in ante de Sitter, there is a natural notion of infrared cutoff, which is really double scale because it's the maximal length an observer can see essentially. So once I'm here, what I'm saying is essentially that the IR cutoff is really of the same order as the UV cutoff. And this is a very problematic situation because typically for a good effective field theory, I would need to require an hierarchy between these two scales. But in these models, by construction, this is not possible. So whenever you find models with this property, essentially with a vanishing gravitino mass on a positive background, well, then you end up here and you have this kind of problem. The model is not protected against corrections, means, if you like, that the model is not a good effective field theory. So this seems an ad hoc requirement, but the vanishing of the gravitino mass, but actually it's not. There are other places in the literature where this appears. This can be also related to the so-called gravitino conjecture. And in particular, all known stable de Sitter vacua in 4-dimensional supergravity with at least 8 supercharges have this property. So as long as you are in 4 dimensions, all de Sitter vacua, which are fully stable and with at least 8 supercharges, enter this class. And for this vacua, you can play this game. You can show that these models are in the swampland for this reason. We investigated also the 5-dimensional vacua. There is only these 2 papers as far as I'm aware of, but I might miss something. And here we were expecting at the beginning to find the same structure again, but actually to our surprise, this is not the case. So for some reason, the de Sitter vacua, the stable ones, there are plenty of unstable ones for which you can apply the argument, but okay, you can always say that these are unstable in any case, but the stable ones, the perturbatively stable ones, actually have a non-vanishing gravitino mass. So there is a fundamental difference we observe between 4D and 5D de Sitter vacua engaged supergravity. And this is something we would like to understand better. So we don't have now a precise understanding of this difference. And again, as for scale separation, the one important missing corner that our investigation cannot cover is the case for supercharges, which at present then, according to this analysis, seems to be the most promising chance to get really de Sitter avoiding this kind of problems. So to conclude, what I showed you is a strategy which is complementary to the standard top-down strategy. And according to this complementary strategy, I really impose the Swampland conjecture directly at the level of gauge supergravity in lower dimensions. And what happens, what we observe is that this supergravity, gauge supergravity, seems already a good starting point in the sense that the results we obtained are not completely off from a Swampland perspective. We obtain results on scale separation in de Sitter, which are along the direction that the Swampland program is pointing to. There seems to be little room for scale separation in de Sitter vacua engaged supergravity with at least 8 supercharges, but still the corner with 4 supercharges is not covered by my analysis. And as feature directions, as I was saying, the analysis was performed in 4D and 5D. It seems straightforward to go to higher dimensions. And it will be interesting to actually investigate better the difference between the 4-dimensional stable de Sitter vacua and the 5-dimensional stable de Sitter vacua, because they seems to have a different behavior with respect to the weak gravity conjecture. For the scale separation case, since I'm in supersymmetric and the sitter, of course, I also have holography as a tool to perform my investigation. So this is something one could look at. And eventually, of course, the main missing corner is, as I was saying many times, the case with 4 supercharges. And to conclude, as a more general question, I would like to pose is that it would be nice to understand whether or not there is a deeper reason why just supergravity, so gauge supergravity plus one assumption, which is the weak gravity conjecture, seems to lead to other Swampland conjectures as well. So thank you for your attention.
Thank you, Niccolo, for the great talk. Are there questions?
Yes. Hi, Niccolo.
Hi.
Yeah, thanks for the nice talk. I think I asked you already, but I forgot the answer. So in the sitter 5 examples, do you know if gauging is suspicious to provide a higher dimensional origin, like having a non-compact gauging or something?
Is non-compact, yes. In the 5D and 4D cases, there is non-compact gauging, usually, yes. Okay, so it's likely that the sitter 5 are in the Swampland as well. Yes, yes, okay. Precisely. Typically, what happens when you try to do the sitter to find the sitter vacuum and gauge supergravity, you typically have to do non-compact gaugings. I'm not aware if there is like a theorem saying that you have to, but in all the examples I know, yes, it's non-compact. Yeah, it's very common. Okay, thank you very much. Thank you.
Okay. Are there any other quick questions?
Maybe something very quick, Niccolo. Can you say something a little bit more about why in 5-dimensional, in the de Sitter 5 case, things are different than in 4D?
Well, just because from the point of view of this analysis, because the gravitino mass is non-vanishing on the vacuum. For really how the vacuum is constructed, you cannot set the gravitino mass to 0 because the gravitino mass is a parameter which is governing the full vacuum energy. So the moment you set the gravitino mass to 0, you set to 0 the full vacuum energy essentially. So you go back to Minkowski. So it's like there is no decoupling between the Hubble scale and the gravitino mass in these models. This is what we observe, but the only thing I can say is that is the way the construction is implemented. I don't have for the moment a more deeper reason than this. In 4 dimensions, instead, it happens that the Hubble scale is something we calculate and the gravitino mass is vanishing. So there is really a decoupling between the 2 scales for some reasons.
Yeah, thanks. So just your discussion is not applicable to 5D exactly because of what you said.
For the stable 5D models, yes. For the unstable ones in which there is a vanishing gravitino mass, it applies instead.
Okay, thanks a lot.
Thank you.
So sorry, I have a question about the reason why you need like vanishing gravitino mass is just like because if you have a vanishing gravitino mass, you get a sharp inequality, right?
Not really, because if I don't have a vanishing gravitino mass, I can always tune one term against the other, essentially. So I want to avoid this situation. Yes.
Okay. Mm-hmm. Okay, thank you.
Thank you.
Okay. In view of the time, let's maybe end the official part of the seminar today and thank all the speakers again.